Hello. In this video, we will be looking at optimization problems in business and economics. We're going to begin by discussing absolute extrema, and then from there, we'll look at different applications and word problems. Up until now, we have discussed relative extrema, but now we want to define something called an absolute extrema. Starting with maximums, a value is the absolute maximum if it is larger than every other function value for every value in the domain of the function, or we might just be interested in one particular interval. Similarly, a function value is going to be the absolute minimum if that value is less than or equal to every other function value for every x in the domain or the interval that you are looking at. We can start by looking at a graph of a function and discuss how these ideas apply in that context, and hopefully that will make the definition make a little bit more sense. So looking at the first graph, we have y is equal to the quantity x minus 1 squared. And if I asked you what is the lowest place on this graph, you would say it happens right down there at the vertex. That happens when x is 1, but the y value is 0. If I ask you what is the maximum value this graph has, you would say there is none, because it keeps going up forever towards positive infinity. So there is no maximum value that you ever achieve. There's always larger values that are possible beyond that. If, though, we restrict the domain of the function and say that you're only looking at values between 1/2 and 2, then suddenly you can't go up forever because you have an endpoint. So yes, we still have this minimum value happening at 0, but you also have two places where the graph gets kind of high. So on the left, it doesn't get nearly as high as it does on the right. So if I ask what's the highest the graph ever gets, you would correctly say this happens at a y value of 1. So the highest it ever gets is 1, and that happens when our x value is 2. If we snip the graph in a different way and give it a different kind of a domain restriction, then suddenly we no longer have the critical value of the function inside the interval of interest, right? Because you don't see the minimum listed that we saw on these other two graphs, but you could still have an absolute minimum and maximum on the interval. So how would we think about that? Well, just looking at the line, what's the lowest we ever got? It was 1. That happened at 2. What's the highest we ever got? That was 4. It happened at 3. So absolute minimum, absolute maximum, absolute minimum, absolute maximum, absolute minimum. There is no absolute maximum. Okay, so that's if you are given a graph, how you might think about them, but you won't always be given a graph. So let's talk about this from just purely the context of how you would do this analytically. So if you only have this function, or this function with a domain restriction, or the same function with a different domain restriction, how do you generate the absolute minimums and maximums? You're always going to start with the critical values of f. Now in this case, f is equal to x minus 1 quantity squared. I'm just going to FOIL that out. That's x minus 1 times x minus 1, which is x squared minus 2x plus 1. So then we can figure out what the first derivative is. F prime is equal to 2x minus 2. And if I wanted to know, like, what are the critical values of that, you set it equal to 0. So 2x minus 2 equals 0. 2x is equal to 2. X is equal to 1. Now, no one is surprised that 1 was the critical value, because critical values always correspond to places where you might have a minimum or a maximum. In this case, we saw that it was a minimum. But if you don't have a graph ahead of time, you don't know if this is a minimum or a maximum. It might be one or the other, or technically it could even be neither. So what it is it's a place where you might have minimums and maximums. Well, that's fine when you're thinking about absolute extrema. So if you have one of these, then this is just one place you have to consider. What would be the other places you would have to consider? Like, in an example when you have a domain restriction. You would also need to consider whatever the endpoints are. So let me go ahead and write that down. Also endpoints. Okay, so I'm going to do the second, or I'm going to go through this process for the second graph and the third graph. What we do if you are trying to find absolute extrema, you just make a table. Your table needs to have x values and it needs to have y values. Or I'm saying y, but just whatever your function is called. Like if your function is called f, then they're f of x values. If your function is called p, then it's p of x values. But you need to have x values, you need to have the function values, and then what you're going to list underneath the x column is every critical value and every endpoint you have. Now I'm going to start with the endpoints because they're endpoints, 1/2 and 2, and then I'm going to ask myself, does my critical value fit in between those? Because if this number is out of bounds already, if it's not in between these, then it's not going to make it on my table. But in fact, 1 is larger than 1/2 and it's smaller than 2, so I'm going to put it on in the table. What we do now is we just plug each of these 3 x values into this function and see what it gives us. So what is 1/2 minus 1, it's 1/2, negative 1/2, square it, what do we get? We get positive 1/4. Well, what about 1 minus 1 squared? 1 minus 1 is 0. When you square it, you get 0. What about 2 minus 1 squared? 2 minus 1 is 1. 1 squared is 1. So looking at these y values are the function values, and one of them is the largest. Here it is. One of them is the smallest. Here it is. So from this table, let me go ahead and do a little bit of highlighting. Let's use yellow for the maximum. So we can highlight our maximum, and maybe we can use blue for the minimum. We would be able to say that my absolute min is 0 when x equals 1. We would also be able to say the absolute max is 1 when x equals 2. Okay, and that would be how you would handle this question if you were only given the function and you weren't given a graph. Well, what about if you were given the information on the far right, where it's the same function but with a different domain restriction, so it has a different interval that we have to consider? Well, you would start the same way. You would start by finding critical values of the function. Then you would come over here and you would come up with a table for your absolute extrema. So you need an x value, you need a y value. Start with your endpoints. So they told me 2 and 3 are the endpoints. Leave a little bit of space because you might have to go slide your critical value in between them. But now that we've computed our critical value, you go and check, like, oh, 1 doesn't fit between 2 and 3. So your critical value is outside of the bounds of the domain restriction they gave us, so it's not actually going to appear here. Okay, but that doesn't mean we can't do this thing. You still plug 2 into the function, which we've already done. 2 minus 1 is 1. Square it, you still get 1. Then you plug 3 into the function. 3 minus 1 is 2. Square it, you get 4. So now you're looking at 1 is the minimum between these two y values. 4 is the maximum between the two y values. So if I highlight in a consistent manner, we have a maximum, and then we have a minimum. And you would want to write a short sentence. So min is 1 if x equals 2. Max is 4 if x equals 3. So that's how you think about absolute extrema and how you would go through that computation. All right, and one more time just to be like super abundantly clear. Your absolute extrema can occur at 2 different places, either the critical values or the endpoints of the function that they give you. These would be usually restrictions on the domain of the function. Okay, so let's do an example. And this just jumps right into application problems. Here, we want to maximize a revenue function. So we have a total revenue function for a blender given by this equation, and we would like to determine how many units will provide the maximum total revenue in dollars. So for part A, notice they haven't given me any type of extra domain restriction. So for part A, if you want to find a maximum of R, we do this like we have done in previous sections, where we are going to start by listing what are the critical values. We compute the first derivative, and then we set it equal to 0. So then negative 0.1x equals negative 25. That means x is going to have to be equal to 250. Now, when we were trying to classify extrema, the next thing we did after coming up with critical values was we listed critical points. Because it's a word problem, I'm not going to do that right away. What I'm going to say is I'm going to say this might be the location of a minimum or a maximum. So we should clarify, based on some type of work that we do, is this a place where we're going to have a minimum value of R or a maximum value of R? It would be very embarrassing if I went to a board meeting and all the work I did was this, and I said, hey, we need to produce 250 units, and then come to find out if this actually minimizes our revenue. You can imagine what type of an impression that would make. So let's do our homework and make sure this really is a maximum before we go ahead and report that to everybody. Okay? How do you know for certain if your critical value is a minimum or a maximum? You can either use your first derivative test or you can use your second derivative test. So a first derivative test looks like this. We try to draw a sign chart of our first derivative. So we start with the number line, we list our critical value, then you pick some number that's larger than 250. I'm going to pick 300. Plug it into your first derivative function, see what you get. If it's negative, we care about that. If it's positive, we care about that. So we got a negative number. Then we do the same thing with a number to the left of 250. I picked a 0. When we plug in 0, we get 25. That's a positive value. So we have a positive value here. And then you have to consider, if your function is increasing followed by a decrease, is this really a maximum? And the answer is yes. That's clearly the maximum behavior. So the first derivative test showed us that we have a maximum value here. You alternatively could use a second derivative test. Your second derivative test will look like this. We begin by just computing the second derivative. Notice that the second derivative ends up being a constant, just negative 0.1, no x. And then you plug 250, which was your critical value, you plug that into the second derivative. So what is f double prime of 250? Well, since it's just constant, then our answer is whatever that number was. But if there had been an x here, you would, of course, multiply them together. You get this number, and this tells you if your function is concave up or concave down. Negative means concave down, which is this shape. If you're looking at a concave down structure where you know that you have a critical value, then this forces a maximum in the function. So you don't need to do the left thing and the right thing. Pick whichever one seems easier to you or more familiar to you. But you do have to do one of these two things. So now that we've done this, we are absolutely confident that 250 is the place where the maximum happens. So let me reread the question. It says, the sale of how many units will provide the maximum total revenue in dollars? We have answered A. This many units, let me call them units, will maximize this function. Second question, we want to find the maximum revenue if production is limited to, at most, 200 blenders. So when we put an extra limit on the function, what this does is it turns it from a relative minimum maximum question to an absolute minimum maximum question. How do we find an absolute max on this interval? Well, what we do is we make a table of x and f of x, and the values in our table should consist of the endpoints of the function. Okay, let's write endpoints down. And they should also consist of the critical values. However, if the critical values are outside the bounds of what we are actually looking at with the endpoints, you wouldn't need to write them down. Okay, let's think about, since this is a word problem and they haven't just given me an interval, they haven't told me what that's going to be, what would make sense? If you are producing an item, the minimum, like the physical minimum that you could produce would be 0. And in this case, the most that they are allowing us to produce would be 200. We are limiting production to be at most 200 blenders. So these are the two endpoints. And then if the critical value was inside this range, if it was in between 0 and 200, I would slide in the critical value, so I would have 3 points on my table. Okay, but in this case, the place where we know that this function will have a relative maximum at 250, that's outside of bounds of what we're looking at. So in this example, we are only going to be computing 2 y values. So you take whatever the x value is, plug it into this function up here. So if I produce 0, I get $0 of revenue. Maybe that wasn't surprising. If I produce 200, let's put that in the calculator. In this case, I end up getting 3,000. So based on the question, we want to find the maximum revenue, and we only have 2 options. Your maximum revenue is either going to be 0 or 3,000, and you get to pick which one looks bigger to you. So we hone in on that larger number. 3,000 is the maximum revenue given the condition that they gave us. So $3,000 is our max revenue. It's a absolute maximum. Now, you may be wondering what happened to the 250. If you put 250 into this function, you will get a number that's larger than 3,000. But the idea of absolute maximums is that they restrict what you're looking at. So even though, yes, putting 250 in here does give us a larger revenue than this, that's just simply not practicable with whatever the physical limitations are in this company. All right, let's go ahead and look at our next example. So this is a style of word problem that is going to take a little bit of getting used to, but we'll walk through it and hopefully it will make sense by the time we are done. A company handles an apartment building with 70 units. Experience has shown that if the rent for each of the units is $540 per month, then all of the units will be filled. But one unit will become vacant for each $10 increase in the monthly rate. What rent should be charged to maximize the total revenue from the building if the upper limit on the rent is $650 per month? So lots of details in this question, and the thing that's going to feel trickiest, I believe, correct me if I'm wrong, is coming up with our revenue function. Now I'm going to start just with words because I feel like thinking about a problem in English typically helps me think about how the math works. So what's actually going on? The revenue for this company is going to be the price per unit multiplied by the number of units. So for instance, if I tell you that we decided to charge $600 per month, then based on all the information here, you would know $600 per month, like per unit, like that's our price. You would be able to figure out how many units were sold, and then we would figure out what the total revenue for the company is. Okay? Well, now that we are thinking about it in this way, we can start to come up with a function that will model this not just for the $600 number, but for any number. We need to come up with a variable, and because of the way that they are describing like vacant units, I'm going to say right at the beginning, let x be equal to the number of vacant units. Now, if you don't have a lot of experience in a math class writing a phrase like this, it's super common. All we are doing here is we're telling everybody what x is before we start using it in the function. So if you know that x is the number of vacant units, that should allow you to come up with an expression that describes the price per unit. Okay? Now, when we think about price, let me go ahead and do a little bit of highlighting here. Price per unit. Experience has shown that if this is the price, all of the units will be filled, but 1 unit will become vacant for each $10 increase in the monthly rate. All right, so the way I'm thinking about this, we have a $540 baseline, like everything will be filled if that's our price that we choose, but we can choose to add on $10, and we're going to do this X number of times. So if I increase the price by $10 one time, I'm going to have 1 vacant unit. If I increase the price by $10 5 times, I'm going to have 5 vacant units. So hopefully you're seeing how X is the number of vacant units, how that corresponds to just setting up the price for this revenue function. Now that we have an expression that describes price, let's go ahead and come up with an expression that describes the number of units. Let's go ahead again and highlight something that helps me think about the number of units. And what I want to highlight is that they told me there are 70 total units, so that's the starting value, but that 1 unit might become vacant if I choose to increase the monthly rate. All right, so what does that mean? How many units do I have? Well, I start out with 70, but I'm going to have to subtract off however many vacant units I end up having. So let's go through just like a what-if situation. Suppose I decide that I want to have 5 vacant units. Well, then I will take 5 times 10, and that gives me the number 50. I'm going to have a $50 increase in my price, and then what's that going to do to the number of units that I'm selling? Well, I started with 70, but I'll have to subtract off the 5 that I had. So with that, I could, if I wanted to, I could come up with my revenue for 5 vacant units. All right, I feel pretty comfortable with this now. So revenue is equal to this function. Now, after this, we're just going to be doing a little bit of algebra. So let's go ahead and distribute this into parentheses. Okay, when we distribute that out, we should get 37,800 plus 160x minus 10x squared. One implication of this revenue function is that if you choose to have 0 vacant units, your revenue would be 37,800, which should have made a lot of sense given these initial conditions. That would be 70 units times $540 a month. All right, now that I have the revenue function, let's go ahead and reread the question that was being asked. What rent should be charged to maximize the total revenue if the upper limit on rent is $650 per month? Okay, I'm going to go ahead and start setting up a table over here, but there's some work I'm going to have to do in the meantime before I finish filling out the table. But what is the absolute maximum revenue? I'm going to think about this in terms of the price and the revenue. And then somewhere in here, we will also want to list down like what X is, like how many vacant units are there. But I'm not necessarily going to start with X. So we could, based on the conditions in the problem, charge $540 as our price. Like that's one option we have. That means no units will be vacant. If we decide to charge $540, then when we multiply these two numbers, we end up getting $37,800 is our revenue. 37,800. Another way of saying that is if I wanted to charge 540 as my price, X would have to be 0 because 0 times 10 plus 540 is how you would get a $540 price. So this implies that X would be 0. If we decide to have 0 vacant units, this is our revenue. Well, we also have an upper limit on our rent. The largest rent we can possibly charge is $650. Maybe there's like a city ordinance that says that, or maybe we're part of a corporation and the corporation won't allow us to charge more than this, or any number of other reasons. In order to get this, how many vacant units would we have? Or if we chose this price, how many vacant units would we have? Keep in mind, you will get 1 vacant unit for every $10 increase in the monthly rate. So between here and here, we increased the rent by $10 11 times because, just compare the number 54 to the number 65. That's a 11 unit difference. Okay, so in order to figure out the maximum revenue, there's a couple of ways we can do this. You can either take 650, that is your price per unit, multiply by the number of units, that would be 11 less than 70. So you can do the computation that way, or once we've decided that, okay, that really means X is 11, you could put 11 into this function. Either way, you should get the same number, which is 38,350. So already, right out of the gate, the company will make more money if we charge $650, even though we have 11 units that are vacant. That just gives us a higher revenue than filling all of the units. But we can't stop here because we haven't actually applied calculus to this problem yet. We don't know, we haven't considered what is the maximum of this function. What is the relative maximum of this function? So the way we do this, I'll go ahead and do this in blue. We are going to come up with critical values. We think about r prime, and we set it equal to 0. So that's 160 minus 20x. That needs to be 0. So if I add 20x to both sides, 160 is equal to 20x. Divide both sides by 20. And then 160 divided by 20 should give me 8. So x is equal to 8. Now, this number happens to be a nice integer. Right now, I'm going to put 8 over in the table, but what if x is equal to 7.6? Like maybe that's how the math works out. Maybe instead of this number being 160, it was some other number so that x ends up being 7.6. Well, you can't have 7.6 vacant units, so if you end up with a decimal in a problem like this, you basically have to consider both sides of it. Well, what would happen if we chose 7 and what would happen if we chose 8? That you don't necessarily know that rounding this like you would normally round will in fact achieve a maximum when you're considering the function. Okay, but this writing in red was just a what if. We're not actually considering that. Where we're actually at is we have realized that 8 units is a critical value. Now, we have not gone through the process of proving if 8 is a minimum or a maximum, and we don't actually need to, because we know that the absolute maximum will occur somewhere in one of these 3 locations. So it's either going to be at 0 or at 8 or at 11. Right now 11 is the winner, but we don't know what 8 is. But between the 3 options, we're definitely not going to choose x equals 0. So what will happen when x is, when x is equal to 8? Well, we can figure out the price. We started at 580 and we chose to have 8 vacant units, so that means we get to increase this price by $10 8 times. So 540 plus 8 times 10 ends up giving us $620. And then we can compute the maximum revenue. So then you can either put 8 into this function or compute it just with some common sense. If you know that the price is 620, and we know that we have 8 units vacant, but 70 units in total. So 70 minus 8 would be 62. We could take 62 times this number to get our answer over here. I'll just go ahead and put it into the function. And now that we've done this, we have all 3 possibilities for an absolute maximum. When you look at these, the one that is the largest is this middle one. So our absolute maximum for this word problem is $38,440. Now, I just want to comment that right now we're handling this from a purely mathematical perspective. We have found the number of units that will maximize this function, which is kind of stale, but there in a real life situation, there are going to be human parameters and maybe parameters for your company that will affect your thinking. So it could be that the company really doesn't want to have 0 vacant units because they might actually want to do some kind of maintenance in between renters. So if they can rotate through, like each of these 70 units needs to be maintained once every like 5 years, if they can come up with a schedule for rotating through, and in 1 year a unit is vacant so that they can do maintenance, that might be a really desirable thing. So that would really steer us away from having 0 vacant units. You might also be in a place where you're providing housing for people who are really like at-risk individuals. If choosing the number 8 means that there's now 8 families who don't have a home and don't have any other prospects, this may not be the moral decision to make, right? You may have increased your bank account by what, like almost not even $1,000, but if the cost of that is like the livelihoods of 8 different families, that's something that you should be considering as you're making the decision. But it could also be that these 8 people, like they have plenty of options. You're not evicting anyone and throwing them onto the street. These people have plenty of options that they will just choose whatever is the best deal for them. And then if we don't have to be concerned about how these 8 people are like spending like where they're living, like what they're doing, then yeah, we can definitely go for the thing that's going to maximize our profit. Now, there is going to be a question on the homework that has a very similar setup to this, but instead of asking about revenue, it asks about profit. So just keep in mind that if you are looking at something that's very similar to this, that's asking about profit, you have to start with your revenue function, but then you would have to subtract off the cost. So if you're going for profit, start with revenue, subtract off whatever the cost function is, and you'd probably have to spend a little bit of time thinking about what would constitute a cost function. All right, but we've already spent plenty of time on this example. Let's go look at the next one. We begin just by reminding ourselves what a marginal profit is. The marginal profit function is the derivative of your profit function. So since it's a derivative, your marginal profit could be used to maximize profit functions. Remember, your first derivative is useful for finding values where minimums and maximums might occur. So we have here a profit function in this next example. Looks like it's a cubic function of some sort. And we would like to have a maximum profit. So let's go ahead and start doing a kind of a first derivative analysis to find out what our critical values are and where we might expect minimums or maximums to occur. We start with critical values. This means your first derivative, so this is your p prime, which is in this notation is the marginal profit, would be equal to 6,400 minus, let's see, that would be 36x minus 3 times 1/3 is just 1, so it'll be minus x squared. Derivative of 40,000 is just 0. So our marginal profit is equal to this. For a critical value, it needs to be set equal to 0. So let me rewrite this. X squared negative x squared minus 36x plus 6,400 is equal to 0. I'm going to multiply everything by -1 because it's going to just be a little bit easier for me to think about. And at this point, you need to solve this, so you either want to factor or use the quadratic formula. Let me see if I can quickly find something that multiplies to 6,400 that will also add, sorry, I need to multiply to a negative 6,400 and then add to a positive 36. 1 times 6,400, 2 times 3,200. I'm going to jump up to 10 times 640. Keep in mind, one of these two numbers will be negative, so if the 10 was negative, it's still not adding to the number I want yet. So let me jump higher. Let me try 50. Not quite. And I could check more numbers along the way, but I'm now noticing that if I picked 100, then I would multiply by 64, and I think this is going to work. So if we subtract these two numbers, we do get 36. I want to get a positive 36, so let me actually make the 100 positive and the 64 negative. So with these two numbers in mind, I would factor this x plus 100 times x minus 64 is equal to 0. That means x is equal to negative 100 or positive 64. All right, so this is a profit function. X is a number of units, so it doesn't really make sense to sell a negative number of units. When we go ahead and we try to find the maximum value, we're going to come up with a table because this is an absolute maximum value. We're going to come up with a table of x values and then p values. So negative 100 was one of the critical values, but it doesn't make sense in the context of the example, so we exclude it. Okay, if negative 100 doesn't make sense as the minimum number of units that you could produce, what number would be a good minimum number of units? How about 0? 0 is an amount of units you could sell, so it gives us a minimum boundary of this function. All right, then 64 is one of our critical values. And lastly, we should consider, did the problem give me any indication that there is a maximum x value I need to consider? And when you read over this problem, there is no, they don't say the company can make at most 2,000 units. No, they just, it's open-ended. So there is no maximum here. So we're going to check this thing, we're going to check this thing, and then we'll talk about it once we get there. So if you plug 0 into the function, clearly this is not maximizing our profit, negative 40,000. What happens when we plug 64 into the function? I get 208,490.67. So $208,490.67. Now, we have not shown that this is a maximum. You can show that this is a maximum either by doing a first derivative test on the critical value of 64, you can do a second derivative test on the critical value, or we could pick another value that's beyond 64, plug that into the function, and see, is this function, does it actually increase beyond this value? If the next value we pick, any number bigger than 64, so we could pick 70, if the next number we pick ends up with a smaller profit than this, then yes, 64 is the absolute maximum of this function. I am a big fan of the second derivative test when you can compute a second derivative. So let's compute p double prime. That would be equal to, let's see, negative 36 minus 2x. And let's then compute what is p double prime of 64. You get negative 36 minus 2 times 64, and it's clearly a negative number. If you care, the value is negative 164, but what this shows me is it shows me the function is concave down. So if you have a concave down function, we can say, yes, this is a maximum. That this process might have been faster than plugging 70 into this function. But in some manner, we do have to verify, because we didn't have a final endpoint, we had to verify that the number we are going to say is a maximum actually is a maximum. Now, being a word problem, you should always make sure you have answered the question before you continue on. They say selling how many units will result in a maximum profit, then find the maximum profit. Let me write a sentence that answers this question. Selling 64 units maximizes the profit, which will be $208,490.67. So, final answer to this word problem is that sentence right there. Okay, let's go ahead and look at one last type of example. We are looking at a firm which can produce 100 units per week of something. Their total cost function is given by this equation, and the total revenue function is given by that equation. How many units should it produce to maximize its profit? Find the maximum profit. So right out of the gate, you notice that there are boundaries on the number of units we are allowed to produce. So my absolute max, there's going to be an X value, there's going to be a profit value. The minimum number of units you could produce and sell would be 0, and they've told us that the most they can produce and sell is 100. Now, we are going to have to do some work and make a profit function. Then we're going to have to take the derivative of it, and we're going to find critical values. And it's probably going to happen that one of the critical values is in between 0 and 100. But if that isn't true, then these would be the two values you would have to consider. All right, but before I get too far ahead of myself, let's think about the profit function. P is equal to revenue minus cost. So then this would be, we're making 1600x minus x squared, and then our costs are 500 plus 1500x. So that's profit. That's 1600x minus x squared minus 500 plus, minus 1500x. As I simplify this, I'm getting negative x squared plus 100x minus 500. Now, don't lose track of what we are doing. You are looking at this equation and it's quadratic, and if you've been in too many algebra classes, you may just feel like I need to apply the quadratic formula to this, I really need to try to factor this, I need to set it equal to 0. Like, if you're thinking that, hold on, this is a profit function. How do we maximize any function? We think about its derivative. So don't do anything more with a profit function. You need to think about your marginal profit, which is your first derivative of your profit function. This is negative 2 plus 2x plus 100. Now, if your marginal profit equals 0, this gives you critical values, which will in turn be locations where you might have minimums and maximums. Okay, so 0 equals negative 2x plus 100. I'm going to add 2x to both sides. 2x equals 100. X is equal to 50. Okay, so this is a critical value. So I guess I didn't write the word anywhere, but let me write it here. Critical values. We go ahead and we put 50 onto this chart that contains all of the points you would have to consider for your absolute maximum. Now that we have that, we can go ahead and we can figure out what would the profit be if I produce and sell 0 units, 50 units, or 100 units. We're going to take these, we're going to plug each of these values back into this profit function. All right, we have computed the y values. Whew, thank goodness we had a critical value, because otherwise we would have had to say that our maximum profit achievable is negative $500. In fact, our maximum profit is going to be $2,000. This happens when we are creating 50 units. So does that answer the word problem? How many units X should it produce to maximize its profit? 50 units. Find the maximum profit, $2,000. Take a moment to write out a sentence that says this. If you look at this table, there is right now, based on the work that I have left on this page, there is no indication that I know what the answer to this question is. Right? Now, you may feel like it's obvious, but only because of the words that I have said. Producing 50 units will achieve a maximum profit of $2,000. Okay, now that we have spelled out the sentence, we have actually answered the question that they gave us. Okay, so now that we've answered the question, I'm going to go on a very small tangent. What if they had asked you for the minimum profit? Well, I mean, that would kind of be dumb in the context of a problem because no one wants to achieve a minimum profit. But aside from that, when you're looking at this table of the potential absolute maximum values, what I notice is negative 500 shows up twice. So if they had asked for a absolute minimum profit, I would say the minimum profit you could ever achieve is negative $500, and there's two ways you can achieve it. You can achieve negative 500 if you produce 0 units or if you produce 100 units. So that would be like the type of sentence that you would write, or if it was a more stale type of a problem that didn't actually like have a context, you would just say the absolute minimum is negative 500 when x is equal to 10 or 100. All right, well, that concludes this video. So hopefully that is helpful as you think about absolute minimums and maximums and how they apply in a word problem context.